Hi, good morning and welcome. Thank you for the introduction. So today I will talk about toward secure and convenient browsing data management in the cloud. So first of all, I would like to very briefly introduce which kind of browsing data may be saved by our browsers. So roughly speaking, we can have at least 3 categories of browsing data. So the first category will be user-saved data. So for example, the passwords for different websites, and the bookmarks, autofill, and autocomplete values for different forms. So that's first category. The second category could be the browser-saved data. For example, could be the browsing history and the HTTP cookies. So basically, browsers will save those data coming from different websites automatically on behalf of us. The third category will be the browser preference settings, such as homepage, language, appearance, security, and the privacy settings. So the third category, those browsing data could be related to the first category and could be related to the second category. So overall, we consider the complete collection of all those data as the browsing data for each particular browser profile for each particular user. Okay, so with all kinds of browsing data, now let's consider what will be the ideal situation for the browsing data management. So the ideal situation will be those browsing data will be securely protected and conveniently accessible to users. So here, by securely protected, that we mean that the confidentiality, integrity, and also the availability of all those browsing data can be highly assured. By the conveniently accessible, so basically we mean for the users, no matter where they will do the browsing on different computers at different locations using different browsers, they can always access the same set of browsing data no matter where they are and which browser they will use. So that's the ideal situation. So we can consider, for example, sometimes we use browsers at home, sometimes we use browsers at office, sometimes we visit our friends, we may use their computers, but always we can securely use all the corresponding browsing data for our browser profile, no matter where we are. So that's the ideal situation. So now let's look at the reality. For the reality, basically, we consider 2 categories of problems. The first category is browsing data insecurity problems. The second category is browsing data inconvenience problems. So altogether, we call them BDII problems. So this table illustrates some examples. So here we have 5 most popular web browsers: Internet Explorer, Firefox, Google Chrome, Safari, and Opera. And we have a few types of browsing data: website passwords, bookmark, HTTP cookies, browsing history, and preference settings. So for example, for the website passwords, we can see for different browsers, they will save the encrypted passwords using different manners. And for example, for the Internet Explorer, the encrypted passwords will be saved into the Windows registry entry. And for Firefox, Google Chrome, the encrypted passwords will be saved to the SQLite database. And for Safari and Opera, the encrypted website passwords will be saved to their specific binary files. This is for one type of browsing data. And for other few examples, different types of browsing data, different browsers they will use different types of files to save the corresponding data. So what we observed is that for the security problem, first of all, for the passwords, for the login information that we use to log into different websites, what we found is that existing browsers do not provide a strong protection to our saved website passwords. poor protection. So in one of our previous existing work published in this year's SM CODSP conference, what we found is that in that paper, what we found is that weak protection. So all the existing browsers, they only provide very weak protection to our website passwords. So here I can provide more detailed information about this insecurity problem. So I would like to use an analogy to illustrate the problem. So we can consider our computer as a home. So computer is similar to a home, and the password manager equipped to all those popular web browsers. We can consider that as the safe in a home. And then the problem is that for some browsers, for example, for the Firefox and Safari, Firefox and Opera, they provide a master password mechanism. So the master password is similar to the combination that can be set for the safe, so in comparison. And what we found is that for three browsers, Google Chrome, Internet Explorer, and Safari, basically they do not provide a master password mechanism. So using this analogy, that is equivalent to, okay, we have a safe in our home, but we are not allowed to set the combination for the safe. And for the other two browsers, Firefox and Opera, they provide the master password mechanism, but they do not make this mechanism mandatory. So basically, users may not use this feature and may not even notice such a feature, master password feature, exists. And that's one thing. And the other thing is what we found is that even for these two browsers with master password mechanism, the protection is weak. Basically, brute force attack is quite feasible. And basically, if attackers steal the stored encrypted data, if they perform offline dictionary or brute force attacks, it is quite possible they can figure out the original plaintext password if the master password is not strong enough. And the other thing is phishing attacks to the master password is also possible. And here I provide one example. So this is here we have two figures. The upper figure basically is a dialog box displayed by the Firefox browser to ask a user type the master password. So quite often when a user for the first time to either save or autofill the login information, Firefox will display this dialog box. This dialog box can be very easily spoofed. The second figure, the bottom figure, illustrates a dialog box displayed by the JavaScript prompt function. So this function can be triggered on whatever websites, on whatever web page. So think about a malicious web site may, at a certain time, display such a dialog box, ask about your master password. So then if a user types the master password, immediately the master password is stolen by the attackers. So basically, these are some existing problems for the protection to the password. Okay, then let's go back to the reality. Again, look at some other problems. So the protection to the website password is weak. And furthermore, for all other types of browsing data, basically all the existing browsers, they do not protect. They do not encrypt those data. That means once stolen, attackers can obtain all the original information of the user. Cookies. And for example, cookies, our browsing history, and our privacy security settings, so on and so forth. Those information, once stolen, quite often will lead to severe security and privacy problems. So that's about insecurity problems. So now let's look at the inconvenience problems. So we have at least three categories. One is poor data consistency. So for the existing browsers, only two or three, for example, Firefox and Google Chrome, they provide a synchronization feature. They allow a limited set of browsing data to be synchronized to their specific servers, and then users can access those data on another computer, for example. But we found is that for both, for example, for both Firefox and Google Chrome, their synchronization have some limitations. So basically, consistency is a problem. Because they save data to the local disk, a user may use the browser on this computer, on that computer, and eventually the consistency conflicts may happen, and those two browsers do not resolve the conflicts in a very proper way. And if you look at search online, you can find, for example, Google Chrome data consistency, Google Chrome synchronization consistency. You can find many discussions, for example. The second problem is poor compatibility and sharing across browsers. From this table, we can see different browsers, even for the same type of browsing data, they will use different formats. And then that means if you want to share the data, the same browsing data across different browsers, it's not that convenient. So some browsers provide the import-export functionality, but on the one hand, they only allow you to import-export a limited number of type of browsing data. On the other hand, users must manually perform export-import. That's one thing. And the last category of inconvenience problem is no synchronization across browsers. As I just mentioned, certain data can be shared. For example, very simple data, bookmark and homepage. Basically, they're just URLs. They can be shared using export-import functionality, but this kind of automatic synchronization is not provided by any browser across different browser products. So basically, that's the existing problems that we identified, we highlight, and we want to address. Okay, so before we propose our solution, so I would like to very briefly talk about the threat model that we consider and some assumptions that we made. For the threat model, so from this NIST Information Security Handbook, we know that when a threat intersects with a vulnerability, security is present. So just now I mentioned about the vulnerabilities, right? Weak protection to password and no protection to other types of browsing data. That's the vulnerabilities. Now if we consider the threats, so where those threats come from and how they will actually perform the attacks. For the threat sources, basically attackers, so who are interested in user-sensitive data, so attackers definitely exist. And so how they can perform the attack? So one typical attack they can perform is that they will install malware, temporarily install malware to a user's computer. For example, using the very popular attacks such as drive-by downloads. So in case you are not very familiar with about drive-by downloads, basically, attackers will host some malicious code on different websites, different web pages, and then when a user click a link, visit those websites, click a link, and then the malicious code hosted on those web pages will automatically exploit the vulnerabilities in our browser, and then will automatically download malicious payload to our computer, and without user confirmation, the malware will be installed on our computer. And indeed, the drive-by downloads is a very severe problem. For example, both Google and Microsoft, they have a large-scale infrastructure to perform this kind of drive-by download analysis, because I want to make sure the search engine results returned those links returned by their search engine. They want to make sure those malicious links will not be returned as top-ranked links. So both those companies have large-scale infrastructure to detect. Okay, then with this kind of attacks, malware is installed, and then in a few seconds, the installed malware will steal the saved data, browsing data saved by those browsers, encrypted passwords. unencrypted other types of browsing data. Okay, so that's a basic threat model. And then here we also have some assumptions. So for whatever security mechanism, we must have some assumptions. So we assume the installed malware will be removed from the system in a timely manner. So here we have some justifications. The first one is, so quite often we install some antivirus software on our computers, right? And for example, Microsoft Forefront Endpoint Protection, which is free. And basically, when those installed malware perform some malicious activity, for example, file transfer, then ideally, hopefully, and this kind of anti-malware software will detect those malicious activity, and then we may perceive the problem, and then we may, for example, we may unplug the network connection, disconnect the internet connection to stop this kind of malicious activities, right? And do some protections. So that's one thing, and or we will clean up our system, rebuild our system, so on and so forth. The other thing is there are many solutions. For example, one example is this Back to the Future framework. Basically, they will, this kind of framework will take the snapshot of the system, and then if some malicious activities or suspicious activity are identified, they can help to restore the system to the previous good state to ensure the integrity of the system. And this assumption, the third point is that this assumption is also made in other systems. For example, Google's two-step verification authentication system. If you look at the research paper, this assumption is very clearly mentioned in the research paper. So because otherwise, if the malware persists in our system, definitely malware will steal the second authentication factor, also our password, so on and so forth. And in another way, we think about this assumption. Basically, we can consider, still go back to our original analogy. So we can consider, okay, a thief come to a home. Okay, so for our basic threat model, we basically a thief may come to a home and steal something and then run away, right? And either noticed by the homeowner or even without the observation from the homeowner. Here the assumption is more, our assumption is more about, okay, the thief will not be there in the home for a long period of time, stay with the homeowner for a long period of time to observe what the homeowner is doing and perform this kind of persistent attack. And the other thing we assume, basically, it's very difficult to identify cryptographic keys from the memory. So even in that short period of time, in a few seconds, basically the installed malware, quite often they will be in a separate process. So cross the process to steal the memory content is difficult. And indeed, there's some research work that want to make this kind of identifying the cryptographic keys from the memory very difficult. So I think this assumption is also valid. Okay, so now let's look at our solution. And first of all, we provided we identified some requirements for addressing the insecurity and inconvenience problem. So here we list a few requirements, but definitely we can have more. The first requirement is about security. So the confidentiality, integrity, and the availability for all types of browsing data. So that's the first requirement, as we just justified. So weak protection to passwords, no protection to other types of browsing data. The second one is ensure the consistency of the complete set of browsing data across for each browser profile across different computers. And as we mentioned, so existing Firefox, Google Chrome, there can introduce consistency in conflicts, and that when they resolve the consistency conflicts, they use different policy. For example, for the Google Chrome, basically they will always, I think they use timestamp, they will always replace the data with the old time step. For example, for Firefox, it will provide a few options, and hopefully, I think 3 options. Hopefully, the user can make the right decision, either to replace the local data or either to overwrite the data saved in the Google, in the Mozilla server side. So different options. So the third requirement is about the synchronization, support the sharing and the synchronization of the complete set of browsing data across different browser products. So as I just mentioned, so the different those different browsing data for different browsers, they have quite different data types. It's very difficult, especially for complex data types, browsing data types. The sharing is difficult, synchronization is not supported at all. And the fourth one is assure the availability and readily use the browsing data available and readily usable anytime, any place on different computers. So right now, basically, Firefox, Google Chrome, they support this kind of server-side backup for certain types of browsing data. The fifth requirement is about good usability with minimal user intervention. And for this one, basically, we want to make sure if we have a new mechanism, the new mechanism will be usable, and it's not users will not make some mistakes, some usability-related mistakes, and which can lead to the security problems. The last one is about follow the principle of least privilege. So I will further talk about details of this requirement in the following slides. Okay, so this is our proposed architecture. So basically, we propose this CAB browser architecture, so Cloud Computing Edge browser. So the basic idea is that here at the local computer, the browser will not save any browsing data to the local disk. So all the data will be synchronized, will be saved to the cloud storage services. Here, the browser side, we have multiple components. For example, the user interface component will provide one single place for user to type the provide the account information and the mask password to protect against phishing attacks. And we have some other components. Basically, all of them are in-memory components to perform the browsing data record management, encryption, decryption, so on and so forth. And then all the users' browsing data records will be protected with authenticated encryption mechanisms, and then the encrypted data will be split into multiple parts, and we will synchronize the data to multiple cloud storage service providers. And in that way, because quite often for the browsing data, the size for each user, the size is not that large. I think quite often, at least for my case, less than 1 gigabyte. So in that case, there are many free, available, widely deployed cloud storage service providers. So they allow users to create free accounts to take advantage of their service. So in this case, encrypted data split into multiple pieces. Each piece will be saved to one particular service provider. And then I will explain how this architecture can, to a certain extent, meet those few requirements. So first of all, let's look at the security requirement. The first requirement, security. So basically, we will take a few different measures to ensure a strong security guarantee. So first of all, as I just mentioned, we require a user to use a strong master password, and the strength of the master password will be assured using, for example, a proactive password checker and with certain length requirements. and this mask password is only known by the user. So we make this requirement mandatory. The second one, encryption mechanism. So from the mask password, we will derive the keys, the cryptographic keys. This key derivation must be strong. So for example, we can use PBK DF2, which is password-based key derivation function, version 2, with randomly generated source and very large iteration counts. So in that case, we ensure a strong key derivation. And in that case, eventually we want to protect against brute force attacks. So to protect against the brute force attacks against the mask password of the user. And the third measure, we will use authenticated encryption to simultaneously assure the confidentiality and the authenticity or integrity of the protected data. And I can tell you, for existing browsers, quite often they do not, integrity is not considered. For example, for Firefox and Opera, and for some other third-party, for example, password managers, they save encrypted data and they will decrypt even you provide some wrong, even the protected data is corrupted, modified, they will still perform the decryption, but definitely the decrypted data will not be, is not usable. So the last one, as I just mentioned, the decrypted data, the ciphertext, for example, we can consider that as ciphertext, will be divided into multiple pieces, for example, 1, 2, 3, 4, 5, and then we will use secret sharing schemes, for example, Shamel's KN threshold scheme, and then save each individual piece to one particular cloud storage service provider. And in that case, even if one single service provider is compromised, or if we have insider attacks for the storage service provider, they cannot decrypt the data to recover the original browsing data of the user, because the ciphertext that they can access is incomplete. For decryption, we must have the key, we must have the complete ciphertext, right? So if the ciphertext itself is not complete, they cannot recover. So at least K service provider, if they work together, they can recover the original data. So for the requirement 2 and 4, basically that's consistency and also the availability of the browsing data anytime, any place on any computer. For these two requirements, still based on our architecture, so we store the data into multiple storage cloud service providers. On the one hand, just now as I mentioned, provide a security guarantee, very strong security guarantee. On the other hand, the availability and accessibility can also be assured. So as long as K service providers can be accessible, the original data can be recovered. And meanwhile, we always synchronize data to the cloud. We do not have a local copy, so the consistency, conflicts resolution becomes much easier for us. And the third requirement, sharing and synchronization between different browser products. For this one, we will focus on the data structure design. So basically, for the record, for different types of browsing data record, and for the concatenated encrypted data record, which is encrypted, for that data object. So we want to make sure the data structure are compatible across different web browsers, and also the data object saved to the cloud storage service provider will be extensible. Basically, the service provider do not need to care about the structure of the data saved to them. And also for the usability, basically we simply use password-based mechanism, and in that case, we do not introduce a new mechanism, new authentication mechanism. And we also we simplify the changes that we make to the system. And so in that case, user can still use the original browser, but with better security and with better accessibility. And the last one is about the least privilege. So basically, without the local file reading and writing operation, we can remove all the corresponding file reading and writing operation from the existing browser. We can get rid of those operations. And remember, for the one motivation in our threat model, we mentioned drive-by download is one motivation, right? One threat sources, one attack that attackers can perform. And here with our architecture, indeed, if we remove those browsing data management related file reading writing operations, we can get rid of a lot of file operations, and basically we can reduce the attack surfaces of the drive-by downloads. Because file operations, reading, writing, those operations is one essential element for drive-by downloads to really happen. They have to save the data, save the malware to the local disk, and then trigger the execution. So in this way, we can indeed solve the attack, solve the drive-by download problem to a certain extent by reduce the attack surface areas. So the last point I want to make is about the.
In the interest of time, we need to wrap up in 1 minute.
Okay. Sure. Yeah, sure. So the last thing I want to say is about adoption, implementation, and deployment. So basically, the security convenience benefits, we think that's the most important incentive for browsers and browser vendors and users to adopt this approach. And then for us, how to build this system, we want to minimize the development effort. So we want to build a wrapper application, and we want to build one shared library. And those two components will work together. And meanwhile, we do not want to make any change to the existing browser. And then with this wrapper application and the shared library, we want to achieve those objectives and meet those few requirements to enhance the security and the convenience of the existing browser, but do not change their source code or binary code. So I think that's all what I want to say. So basically, we highlighted the security problem, and we provide one cloud-based solution. Yes, please.
So the user provides a password, and you check it for strength, right?
Mm-hmm.
And you derive the keys from that password.
Mm-hmm.
Is the password or the key stored anywhere, either in the cloud or the local computer?
No. Neither the master password nor the derived keys will be persisted to the disk or to the cloud. So they will only exist in the memory. Yeah.
So they exist in the memory of the local computer?
Yeah, memory of the local computer. Yeah. The master password must be remembered by the user.
What if the user forgets their master password? Does that mean they lose all that saved data?
So far, that's true. So if the user forgets about the master password, then so far we don't have a good solution to recover.
If I may interrupt, could we keep the Q&A offline since we run out of time? Sorry about that.
Okay.
All right, so let's thank Chuan for his talk.
Thank you.